Hello students, today this is the fourth class of our January 2022 NET online crash course, and we'll be discussing central force. This is the part 2 of the central force. Part 1 of the central force was already discussed in class 3. So today we'll be discussing the other aspects of the central force. See, in the last class, we discussed the capture by the potential. And today, we will be discussing how Earth itself can have a comet crash on it. So let's start with this example. A small meteor approaches the Earth. I'll have a little bit of zoom. Okay. A small meteor approaches the Earth. When it is at the large distance, very large distance, it has velocity v infinity and impact parameter b. We already discussed what an impact parameter is in the last class. If re is the radius of the Earth and v0 is the escape velocity, this will have a relation with escape velocity. The condition for the meteor to strike the Earth is etc. etc. This was asked in TFI 2010, and this is a very important problem of practical approach, practical implications. A small meteor approaches the Earth. You see that small meteor somewhere. It is not directly on the line of joining. Its velocity is not directly in the line of joining to the Earth, but it is have a impact parameter b. We already discussed it, so we may have a I will delete this slide. So you are at Earth. Somewhere there is the meteor. The velocity is not directly in this angle. This is the line I'm joining. The velocity is like in this way. So how can we calculate the impact parameter? We will extrapolate this. The lowest distance will go, see, well, this is your b. So we'll discuss it. Also, we will have an option. This escape velocity, you might remember that v escape is 2 gm by r. Okay. So effective potential we already discussed effective potential like this. So how will be the effective potential, like this will be like this. So there won't be a capture like that. If we ignore the effect of the atmosphere and the energy loss due to friction, the initial energy is positive for the approaching meteor, and there is no capture like the previous problem. That 1 by RQ potential. If you did not watch the last lecture properly, then it is kind of foreign words to you, but you should watch the lectures in sequences. So okay, each and every lectures are connected. So initial energy was positive, but still the meteor can hit the Earth, rather touch the Earth in a hyperbolic orbit. So here the orbit will be hyperbolic and just touch the Earth, and we will see how can it touches the Earth. Okay, so when it is a large distance, it has velocity v infinity and impact parameter b. So if we take the mass of the meteor as small m, the initial energy is to be half of mv infinity square, as at infinity there is no potential energy contribution. Okay, so this is a diagram. So this is the radius, this is Earth. Okay, here it is a large distance, this is a large distance. So this is for several impact parameter. So if the meteor was at the line of joining, just at the line of joining, then it could have hit the earth directly. But as it will have larger and larger impact parameter, means its initial velocity is larger and larger far distance away, larger angle away, so then its probability of hitting the earth decreases. So there will be a critical impact parameter for which it will just hit the earth. Above that it will miss the earth, so it's kind of just touching the earth. Okay, we'll do it. First, the angular momentum L is mb v infinity, which remains constant, of course, due course of motion, because it's a central force. It's always very important to check that your angular momentum is constant. Okay, the distance b between the initial trajectory and the line A is called the impact parameter, as we already know, of the trajectory. The largest value of b is indicated b dash in the figure. So, if the particle touches the earth, if the particle just touches the earth, then the kinetic energy when touched, it is 0. Yeah, surely it is touching here, so just landing politely. In other cases there will have a kinetic energy, so just touches, so its kinetic energy is 0. So this is the point, touching. And this is missing the earth. And going with a parabolic trajectory like this. And this is direct hitting. So if the kinetic energy is 0, then the potential energy is not only this is what? This is the gravitational potential energy minus gmm by r, plus this is a centrifugal force L square by 2m r e square. This will be there. This will be there. This is the potential energy due to attraction, and this is the potential energy due to mv square by r. This L square by 2m r square. This is mv square by r. We already discussed 2-3 times in our previous problems. So this energy will be there. This is due to the rotational velocity, due to the centrifugal forces. So this will be always there. So this is, as a whole, this is the effective, because the total energy is, we have already seen. I just show you there. You always forget. So what can I do if you forget? The kinetic energy is this, half of mu r dot square plus half of L square by mu r square plus Vr. So if this kinetic energy may be 0 r dot, but both these two terms will be there in the energy expressions. So just don't do a mistake like this. I know many people will give you a mistake if you just say that what will be the energy when it just touches it. 99% of the people will just see this term, but this is the centrifugal term, which is always present in the central force problem. This is a central force problem. This is a one body equivalence of a two body problem, so this will be there. Okay, so then that much of energy will be equal to the energy at the long distance, because energy is conserved. The energy when particle was here, it is the same as energy when the particle is at there, because there is no energy loss. Central force energy is conserved. So this is energy conservation. We need to substitute this L, the value of L here. So then we get B dash is RE1 plus 2gm to this. Just put L here. Then you get B dash. Then use escape velocity expression 2gm by R. Then you get this B dash is this. So do this little math. I always like writing this common error. Okay. And for the particle to be captured, this B dash is the maximum value of B we already discussed. So to hit the earth, your impact parameter must be less than this B dash. So this must be less than RE square root of 1 plus V square by V infinity square. So this is a typical problem of the central force. So means this is a very important practical problem. So do this calculations by yourself. Do always remember the total energy expression. There is an centrifugal term, don't forget it. So we will have applications of this type of problem later also, but first we go to a special force, that is inverse square law. So what is inverse square law? Inverse square law is the common law that gravity, Coulomb's law, both this is inverse square law, where force is varied at 1 by r square. Attractive inverse square law, not repulsive. So that is why the minus, the potential energy is also at minus k by r. Okay. If the circular orbit is there, so we just have a reminder that for circular orbit the force is we discussed in the last class, the force should be equal to mv square by r. Okay. We know we will have some important results first. As we know, the energy for inverse square law in a circular force, this is k by 2r naught. Elliptical force, this is minus k by 2a. Sorry, elliptical orbit, this is minus k by 2a. That k is for the gravity, it is gmm. So k is that constant. Ellipse is minus k by 2a, where a is that semi-major axis. Parabola, the energy is 0. Hyperbola, the energy is positive. Eccentricity for circle, it's defined as 0. Ellipse, it is less than 1. Parabola, the eccentricity is 1. Hyperbola, the eccentricity is greater than 1. So this is a set of common result which you will be remembering always. Just have a look at the virial theorem before you go to in-depth study of the inverse square laws. In my notes we have this virial theorem, so let's remember that it's applicable only for not every system, only for periodic and bounded system. And the theorem is if there is a central force Fr which is proportional to r to the power n, so that the potential energy, this Vr, the potential is proportional to r to the power n plus 1, then the average value of T is equals to the n plus 1 by 2, this is a factor, equals to the potential energy, the average value of the potential energy. It's sometimes written as also like this in other books also, like this, and this bar or this angle forms. This is called a time average, and it's applicable only for the periodic system. So it's 0 to t, some function ft dt by 0 to t dt. This will, for a periodic function, this will just be a t, capital T. This is integration over one time period. So this is the time average defined for any function, any periodic function. Just okay. So this will be using in many problems. So the detailed discussion is already there in my notes, so just check that. Okay, so now we'll have this inverse square force discussion. First look, this is a ellipse. This is a ellipse. This is a center. This is a center. Origin. Okay. This hang. Sometimes it does. This is not the origin of the central force. Origin of the central force will be at the, what to say, I forgot the point, the name of this point, epicenter or something. Okay, this is geometrical origin, and this is central force origin. From this we will define r like this. If the particle is at any point, so this is the distance r, the angle, this is the theta. The r comes at minimum distance at here. This is r mean. This is called, I think, perigee or apogee. I will tell you what exactly it is. And from here the maximum distance in this elliptical orbit will be here. So this is at r maximum. So from the origin of the central force, the particle travels in a elliptical orbit around this central force center. This is the force center. So we have two positions, once where this r is minimum, another where the r is maximum, and we define this semi-major axis 2a from this r max and r mean. So r max plus r mean is 2a, and along the y-axis at geometrical structure, this will have a 2b. So this is a geometrical structure of an elliptical force, elliptical orbit. Okay, then we have some general equation of an orbit under inverse square force. So as you already have studied, that general equation of an orbit under inverse square force is alpha by r is 1 plus epsilon cos theta. Inversely, r equals to alpha by 1 plus epsilon cos theta. So what is r? R is this L square by mu k. L is the angular momentum, mu is that effective mass, k is the force. Don't forget the rule of k here. K is very important. Eccentricity is to be calculated as, you always remember this expression, eccentricity can be calculated as 1 plus 2e L square, angular momentum squared, by mu k square with the square root over it. We define that semi-major and semi-minor axis. There is a calculation involved, but I don't ask you to do all these theories right now. You just remind this as important results. So the semi-major and semi-minor axis, A can be calculated as alpha by 1 minus e square, and this can be calculated as k by 2 of modulus of the energy. So here we will get an energy expression. E is k by 2a. So I would write this in the next page also. Did I write it? Yeah, I should. I didn't. Yeah, this is there. So I should mention it here also. So from here we get energy will be negative, so that's why we are putting a mod there. B is directly related to the angular momentum L by root over of 2 mu e. Remember this because sometimes it might be required. Okay. There will be another results. Oh, this is center of attraction. This is the focus. This is the focus. I forget this term. I remember this term, but at this time, this term just didn't came at my mind. So this is, I will write there. This is the focus. Okay. We already discussed ellipse. Sorry, this is a repetition. I already discussed. Time period of the elliptical orbit is tau is 2 mu by L into A. A is the area. This is very important result. The time period of the elliptical orbit is 2 mu by angular momentum into A. A is the area. A is the area. So this will be 2 mu by L pi AB. I will this. I will write this as again just to keep you. Just draw your kind attention here. This is pi AB. Sometimes I do repetition to have your attention. I don't know. Ignore all this numbers of equation because this is directly from my notes. So just updated note may have a different equation structure. So just ignore this. So well, we get this. Now if we substitute the value of AB from these results, so we get the time period as pi k square root mu by 2 energy modulus to the power minus 3 by 2. So it's this time period depends minus 3 by 2 power with the energy. This also might be useful at some times. So I just covered all this, tried to be. Period can be also expressed as like this. Tau square is, you know, this r to the power cube. So for circular orbit, for elliptical also, Kepler's law, tau square 4 pi square mu by k a cube. So hence it may come at 4 pi square a cube by gm2 if m1 less than m2. It happens always, as the sun is very greater than the earth. So this is like this. So then here it is of very much importance, the maximum and minimum value of r max. This can be shown just from this equation, that the maximum value of r should be alpha by 1 plus e, and the maximum value of r should be 1 minus e, as this denominator should be small, and the minimum value of r should be 1 plus e, because the maximum and minimum value of cos theta will be plus 1 or minus 1. So the maximum value of r is alpha by 1 minus e, minimum value of r is alpha by 1 plus e. This is seen as a into 1 plus e, a into 1 minus e. A is the semi-major axis distance. Okay, total energy for the elliptical orbit we already calculated and already shown you, like the gmm by minus 2a. So energy is conserved, so the total energy can be equated with energy at any time when the mass is at distance r from m, that is center of attraction. So this minus gmm by 2a, this can be equated with at any time with the energy half of mv square minus gmm by r. When r dot is 0, this will be at some special positions. Which special positions did I show you? No. Okay, so I should go back there. So these are the two positions where okay, these are the two positions when velocity is tangential to the line of joining directly. So here r dot equals to 0. So at perigee and apogee, we will take this r dot is 0 at r max at mean, and the angular momentum is to be mv r. So when r is at max, angular momentum is at mean, sorry, velocity is at mean because angular momentum is constant. So here also there will be mv max r mean. So this will have applications of this total elliptical structure in 2-3 problems we look around. Okay, this is some useful data. You need to always remember that the angular velocity of Earth is to be around 7.29 into 10 to the minus 5 g into me, this mass of Earth into g is like this. Within 2% error, this is approximated at 4 into 10 to the power 5. Okay, so these are 1-2 numericals where we will have applications. So let's see what the numericals are. A particle moves in an elliptical orbit in an inverse squared law of central force field. Yeah, if the ratio of the maximum angular velocity to the minimum angular velocity of the particle of the orbit is n, then show that eccentricity of the orbit is like this. So whenever in an elliptical orbit there is a maximum r, maximum velocity, minimum velocity, maximum angular velocity, minimum angular velocity, you just go to this figure and your r max and r mean is this. So here this is the 2 points where all your velocity, angular velocity and the radius vectors will be minimum and maximums. So we start with the equation of the orbit. Alpha by r is 1 plus epsilon cos theta, where r is this, where alpha is this and epsilon is this. We started with this, so always you start with this, then we'll discuss. L is mu r square theta dot, you know. So r max is alpha by 1 minus epsilon, r min is alpha by 1 plus epsilon, discussed. So we have omega, this theta dot is omega. Omega is L by mu r square, from which we get omega max will be alpha by mu alpha by 1 plus epsilon whole square. Omega mean is L by mu alpha by 1 minus epsilon, because omega max will be when r is minimum. So our minimum value we replaced here. So omega max can happen when L by mu r mean, minimum value square, and omega mean is of course L by mu r max. whole square. So we just R mean as R max we replaced here. R max is replaced here. R mean replaced there. So then omega max and omega mean, we just took the ratio. So that give us 1 plus epsilon by 1 minus epsilon whole square, that is n. So hence we will get the answer. What was the question? Eccentricity of the orbit. Okay. So omega max by omega mean, if this is the n, then we can get omega 1 plus epsilon 1 minus epsilon square root of n. And again here we took it minus. So 2 epsilon by plus 2 root n minus 1 by root n plus 1, like this. Okay, so then another problem which always comes, that what is the ratio of R max, perigee and apogee ratio. This is 1 plus epsilon by minus epsilon, just from this to the result. This will be required anytime. So just these results will need it. We will need always perigee apogee. From perigee apogee given ratios, we directly calculate the eccentricity, and from there we go to the energy and moment, angular momentum. So these are the tricky results. After we do this type, we did this R max R mean problems. So there will be many other types of problems. Most of the problems can be divided by this simple 2-3 types. One is like we have R max R mean. You always remember this V max V mean. This is maximum and minimum value, so don't confuse with it, like R P, R apogee, R perigee. That will be inverse of R V apogee, V perigee. That is, perigee is smaller distance, right? So that is R max is that is R P. R mean is R apogee. V max is at R mean, where R mean is R apogee. So that's V apogee. V mean is at V perigee. So in any circle, so this is the focus. This is perigee. This is apogee. So as we have discussed earlier, that at these 2 points, we have special this we can say here R dot equals to 0, so your L is MR P V P. Here also R dot is 0, and is MR A V A. This MR A V A is always MR P V P. So this can be equated with always this to be equated. So examples you will see there. Energy expression also, this minus GMM by 2A. This should be equated with at perigee and apogee. R dot is 0. So energy becomes half of MVR means P square minus GMM by RP, like this, both here and here. So this energy should be equated with half of MP square minus GMM by RP. This should be equals to again with V square minus GMA by RA. So all these things will have applications. I have many problems, 3-4 problems done with my notes, and you will have few exercises in your previous year's problem sets. So if many times you are given at, say, RP given, I just showing a type RA given. So just from this you can calculate your what x2a is RP plus RA calculated, and from here you see RP by RA is 1 minus E by 1 plus E. Here you calculate E can be found, and the ratio of VA VP found, and this VA RA is VP RP. So with this this RA by RP is VP by VA. So here other data with using other data we proceed. So this is just a typical type. We get energy expressions. So I will show you. There are some problems where we left this. Okay, this is the problem which we discussed. This is the problem we discussed just before. There we discussed this theories, these equations, this expression. Well, we have this other problems which each and every problem I will not discuss here. So you go through each and every problem. You have this note uploaded in the Google Drive, sorry Google Classroom. So you go through each and every problems. Okay, this problem, each and every problem will be interesting. I tried to accommodate every types as far as we could. This problem will have a little bit of mistake there. This is not 6.59. Let me do this. This is 6 point. This problem will have a little bit of calculations, so should be very careful with this. 35022 should be 535455557. 57, not 6.59. Okay, this is fine. This is easy. This is also very easy. Do this. This will be little bit of extra things are there. So this is very important. This 3.59. This is important. You go through all this. If you have any problem, then you will discuss in our Facebook group. So this is a very typical and very important problem. Elliptical orbit of perigee and apogee is given. This is typically the data we have before the satellite is launched. It's a very practical approach. Mass is given, so all this. So then step by step, how much energy is required to launch the satellite, and what is the energy in the elliptical orbit. Then we need to transfer the satellite into a geostationary satellite. Then how much energy will be necessary to put. So this example 5.19 in the notes should be very important. So do it. You have the solution within your hand. So do it and understand it. And again, we discussed in this class also that the energy, there will be a centrifugal term. Which problem we discussed? We discussed here in the very first problem itself. We had this centrifugal term included. So we should have this centrifugal term included. So then you calculate this. So the transfer have some little bit of theory, you may skip it and just by energy conservation formulas you can do it. So okay, I will not discuss all this because we don't have much time. There I can discuss, but you may also feel bored. You don't watch the lecture in full, I know. Because okay, so whatever I wanted to tell, I tell you. So this problem will be important. So this problem will be important as I show you the first part and the second part. Okay, let's discuss it. Okay, so can I discuss this in detail? The satellite have some perigee and apogee distances given. So mass is given, radius of Earth is given. So how much energy is required to launch the satellite? And what will be the energy of the satellite in the elliptical orbit? So as you see, this is a practical problem. The ISRO guys need this problem to be solved because yeah, we want a satellite. We want a satellite to go to a perigee and an apogee above the Earth. We know how much the mass of the satellite will be. Then we should calculate that how much energy will be required. So okay, we'll have certain shape like this. Okay. We should not have a fill. So this is say my Earth. This is the perigee. This is apogee. So these datas are given. So this 2a we can calculate. So this is what? This is something given. This is something given. Plus this is 6,400. So perigee, apogee. So total 2a is that perigee 1100 plus that perigee 35,850 plus this 12,800. So something you get like how much? 35, 36, 900, 47. Geostationary satellite. Okay, we need this. So this have okay, 2a is this 5 into the exact. In that we may approach in a different ways. So this will be 5 into 10 to the power 7, right? 37, yeah. Approx, because this is not exact, but yeah, we might have exact calculations there. 1100 plus 35,850. That was the given data. Different you approached here differently, we may approach here differently. Plus 12,800, 47. This is not 5, so this data might be a problem later, because you need to be exact, you need to be precise, otherwise you may have a wrong. 49750 kilometer. So this again we might have a problem there, so be careful with it. How much we have? 49750. Okay, then you can proceed. What we need, GMM we have, so just we needed to 2A there. So the energy in the satellite, how much energy is required to launch. Okay, so, but just calculating 2A, we what we achieved, energy of the elliptical satellite, energy of the satellite at elliptical orbit, GM by 2A, that is, we know GM should be approximately 4 into 10 to the power 5 kilometer, right? GM is 3.986 and 10 to the power 5 kilometer. So if we use kilometer everywhere, both in velocities and distances, then it's fine. So 3.986, we discuss everything is in kilometer, right? Kilometer, all distances, everything, all velocities, all length unit is in kilometer. So mass is 2000 kgs, right? Mass is 2000 kgs, and this 2A is 49750 kilometer. 49750 kilometer, both are in kilometer. So you get the energy joule, that kilometer unit cuts, so no, that's kilometer cube, so there will be answer will be kilometer square. If we want an exact joule, so then you should have 10 to the power, this kilometer will be in meter, but that 10 to the power 5 will be 10 to the, again 10 to the power 3, 10 to the power 3, 10 to the power 9 meter. So okay, in like joule kilometer square kind of thing, and if you want an exact, okay, there was 10 to the power, hey man, there was a 10 to the power 4 or 5, 10 to the power 5. Okay, and if you need in other way, so you could have 5 meter 3 kilometer cube, so that should be a 9 and 2000, 49750 into 10 to the power 3, that is joule to meter something. This kilometer to meter, I always prefer to bring everything in meter, so this you can do. And energy at the orbit is minus mgr plus half of m r square omega square, that is L square by 2m r square, so that is joule. So it is, we don't do this, do this only. So this was cube and this was kilometer, so that is not good. Okay, don't do it. I go in this way, and that orbital energy you can calculate, sorry, orbital energy we have already calculated, ground state energy you can calculate. This you can calculate. Okay, Re you know, omega you know. So this is okay. You calculate this and calculate this. This will be approximately how much? 10 to the power 10 joules. So lunch will be orbit minus ground, like this. This will be minus 125 into 10 to the power minus 11. Be careful with this. Do this. Don't just believe this data in the solution. There might be a little bit problem as we approximated this in the notes a little bit. So calculate this and verify. That is E orbit. Now calculate and verify. This will be the first part. The second part will be this. So verify all this. I did not do it in full. I just given you a thrust. I have given you the thrust. We generally give satellite a thrust. So this is also a practical problem. We transfer the satellite into a circular geostationary orbit above that. How much energy is required to put the satellite, and how much velocity thrust need to be given. So if we have a kind of I'm sorry. So see, in a circle, if you have an elliptical orbit, and if you have a system like this, so now we want to put this. This is how usually things are done. So now we want to make it at a circular orbit. So we need to give a thrust. So the first one thing I will say that calculate. We have a calculated elliptical. Now calculate E circular, because you have the data, you know that will be that apogee distance R apogee. This will be the R of circular. Now that's right. We now want to transfer the satellite into a circular geostationary orbit of this. So you calculate the energy of that circular orbit, what it would be, and what is our elliptical orbit energy right now. Then you just keep this energy differences, and that will be the how much energy is necessary. And the last part, we'll have a little bit of theory discussion. If you want, then you see that what is done. Otherwise, you can skip. Okay, brothers, that is our discussion of central force part 2. We have in the next class will be on Lagrangian, suppose. Yes. Next. So next class. Watch the videos in full. Otherwise, that won't be that much effective. Okay, we have all the problem sets already uploaded. So you do that problem sets. I won't be discussing the problem sets right now. So okay, you will have that problem set. So please solve the problem sets. Okay, so you have our contacts on this page. You know everything. You join the Google Classroom with this code. If this code is not working, then the class is full, then you will need a second code, so that will be there in the video description. Don't worry. if you have reached this that much part of that lecture, so you will be getting that code below in the description if this does not work. Okay, so that's all for today. Thank you.